Okay, so let's go. So today we're going to have a lecture, maybe today and next class, I think. Let's see, I don't want to rush, where we're going to see lots of applications where the material of the course will make you understand better and better the applications. It might, the texts, advanced texts related to it, most of the things I'm going to show, maybe we're not going to see everything in the course. Maybe you won't learn everything about these articles, but definitely you will learn enough in the course to read these articles, right? And that's how we prepare ourselves for research. We're always reading and learning. Okay, so display some applications, as I said. And as I said, let's see here. The course, this is slides I used in the course when I taught abroad. Theoretical, but we'll connect with application. All right, and we'll see all these things about all, as I mentioned, hyperbolic, elliptic, and parabolic in a combined way. Okay, so I work with waves. I work with water waves, okay? Maybe I'll take my gun. I work with water waves. And as you will see at some point in this course, we're going to talk about scalings, about making the equations dimensionless, without physical dimensions. Basically, we're going to go to a setting where it's almost like a canonical setting to study the PDE, the equations. So let me talk about big waves. And I'm going to talk about two different big waves, which means from the PDE point of view, it's different scalings. So this is a huge wave, famous huge wave, Nazaré in Portugal, where surfers, fearless surfers, surf these waves, which are about 27 meters high, gigantic. And why do these gigantic waves form, right? They form, and that's one thing I work in there's a lot of things in my work, which is, and you will see a little bit of this, which is variations of the topography. Variations of the topography, so here's the bottom of the ocean near Nazaré. There's this underwater canyon, and that's why these gigantic waves form. There's a sort of a focusing of energy here. The waves don't break because it's not shallow. It's shallow here and here. So you see here it's 300 meters deep, all the way near the shore. So these monsters go and go and go and go, and they're very fast. So with burgers, you already saw that this is more complicated than burgers, but you already saw that wave height makes it move faster, right? And therefore, these guys can only get inside the wave if they're towed by a jet ski, right? Because you can't swim and catch the wave because it's so fast. Now, the depth makes, as you'll see this later, the depth also affects the wave speed, even in the linear model, right? Burgers is a nonlinear model, but it's a simplified model. So we're going to see there's very much interesting problems, many interesting problems with potential theory, which mixes waves with Laplace equation and so on. You'll see this, okay? So this is one thing, Nazaré, huge waves, and it's due to the topography. So this wave is huge, okay? Now look at this wave. This wave is big, very big. It looks like a nice surfing day, okay? Waves breaking, look, breaking nicely to the right, to the left. Surfers like that. These waves are big, probably 8 meters or so, 10 meters, smaller than Nazaré, but these are huge waves and dramatic huge waves. Sad, dramatic huge waves. Why? Because there's tsunami in Japan, right? And I'll tell you why they're huge and why they're so bad. So look, they come and start inundating, look, getting into the city. There's videos on YouTube, dramatic videos of the water coming in, nonstop. Why is that? What's the difference between these two huge waves? And if you're dealing with PDEs, where is the scaling? Where are the epsilons going to come in differently, right? And we'll learn how to scale the PDEs. So you see, when an epsilon comes in here or there, it tells you which terms are more important in some sense than others, or are order one, are more effective for something. Sometimes not even all might be important, okay? So here is something from the internet, which is a great picture for what I'm trying to say. Two huge waves, okay? The Nazaré is very large amplitude, and tsunamis is very long wavelength. A tsunami is generated by underwater earthquake. And it affects a very big area. And a tsunami, when it's generated, It has a meter and a half high, okay, of height, but it's over like 50 to 100 kilometers. So that's where this danger comes in. It's very scary. You cannot see it from satellite, right? You can see a height of a meter and a half varying over 50, 100 kilometers. You can't see the deflection right of the surface. And then when it comes near the surface, because of the change of speed, the amplitude grows, okay? So there's this effect. So what happens is that this wave here, it's huge, it breaks, it washes the shore, as we see here in Rio. The water washes the shore and comes back in small waves, just a few meters, okay? But the tsunami, because it's a very long wave, it breaks, and then it's almost like a moving waterfall, right? That wave breaking, and the water comes in, because the wave is very long. So because it's very long, it washes in, and then it washes out, okay? Of course, at some places it gets stuck because of whatever, the topography. So this is the difference. So we have to do scalings here. So if here in the PD for this guy is the scaling, which gives you nonlinearity. Okay, we'll see this in the future. Here's more just pictures today. It's amplitude over depth. And the amplitude over depth, if it's not a very small epsilon, your equation is nonlinear. Sometimes 0.1, your equation is nonlinear, and it breaks. And okay, and here it's basically depth over wavelength. So for a tsunami, that's the epsilon for the tsunami. It tells you if you're in the linear and nonlinear regime. Look at this. For a tsunami, the depth, usually when it's generated with an earthquake, sometimes it can be, for us, very deep, like 4,000 meters. The earthquake, the submarine earthquake is 4,000 meters deep. Huge depth, right? But from the model we'll see later on in the course, it's a shallow water regime. What do you mean shallow water, which means small depth? Because the tsunami is 100 kilometers long, so 100,000 meters long. So 4,000 meters divided by 100,000 meters is a small parameter. We'll see this, okay? Now it's just words. So, okay, so one problem that I studied in my PhD was waves over a random medium. So what is waves over a random medium? Well, my advisor, Professor George Papanikolaou, is a world expert on waves in random medium, and his interest was waves in random medium, as I'll show you later, which are pressure waves in the crust of the Earth related to oil exploration, right? Understanding how a wave propagates in a random medium. The Earth is not really random, but there's uncertainty because you don't know if there's oil, and you can model it as a random medium. So therefore, you know what's happening over a certain class of problems or a certain class of speed variations, okay? So in my thesis, we tried to sort of, start importing technology, mathematical technology, from the PDEs of acoustic waves. I'll show you this in the course maybe in 2 weeks or so. Compare a water wave PDE with an acoustic PDE. They don't look that different. They're hyperbolic and blah, blah, blah. And to see what happens for water waves. So here's an example. I found a book during my thesis, which is an oceanographic book that showed the variations of the topography between these two islands in the South Atlantic. See, here's Argentina in the South Atlantic. And here's the map. It's basically the depth doing this trajectory here. So like, you open up and here's the depth. Look at the depth, how it varies in a sort of quote unquote crazy way, right? So you can model it as a random topography, right? And so, for example, piecewise linear, So piecewise linear with a random height, right? And the wave, and this is where the scaling, the dimensionless PDEs and so on, as we'll learn how to do, which is very simple. It's just chains rule, right? You choose a scale, blah, blah. Because of a tsunami, this is a few kilometers or 100 meters variation, but it's the microstructure. Why microstructure? Because it's rapidly varying with respect to a tsunami, which is 100 kilometers, right? So we're going to see problems where there's a periodic microstructure, which is something that varies periodically. Not the case here, but mathematically it's interesting to make a depth that varies periodically and rapidly. We'll see this based on a paper of George Papanicolaou with Ruben Rosales, which is now a professor at MIT, was a postdoc at Courant with George Papanicolaou. But here, you can model this as a random topography. So you see like many things from mathematics coming together, right? And you can do computations with this too, and write equations and so on. Okay, so here is the problem I did many years after my thesis, because it was like one problem coming out of another problem and so on. When you solve a problem, you not only solve a problem, but you discover there's like 3, 5 interesting problems to be done, right? You open the door and say, whoa, there's 5 new doors to open, right? Some people might say, oh my gosh, now I have to do this. No, well, and if you have students, it's a lot of fun, right? You discover things. So many things, and related to the group of Papanicolaou, this is a simulation I did with some colleagues. So this is basically here a synthetic random topography. Why is it synthetic? Because I do it, right? It's not real data, right? I just use a random number generator, say with MATLAB, and I put random heights and connect them with a line. It's a piecewise linear random topography that looks like the one I showed you from the book, which was real, but this one is synthetic, right? It's just for us to test mathematical ideas and see if things work or not, right? So this is a detail, a zoom of this region here. Here's my synthetic, say, tsunami, just a wave, right? It's very convenient mathematically. It's very useful mathematically. Sometimes if you want to work with a pulse, which is a wave, just a slight, sort of single wave, to work, as I mentioned, in Burger's equation, with a Gaussian. In this case, it was actually more interesting to work. I cannot quite explain here, but it's because Fourier spectrum is a little richer, which is the derivative of a Gaussian, so it decays a little slower. So this is the derivative of a, oops, I'm still not getting with the right. So this is like the derivative of a Gaussian. It looks like a real wave, right? And you see, look, it's a long wave with respect to the microstructure, right? And many, many interesting mathematical and physically relevant phenomena appears in this problem, and we're able to understand it mathematically and provide evidence numerically. Mathematically, using asymptotic theory, not everything, of course, is rigorous because the problem is very difficult to prove theorems or what, but it's right. But we use some rigorous tools at some points, including with my probabilistic colleagues that I interacted, which were Jean-Pierre Foucault and Jocelyn Garnier. So look at one phenomenon that we were able to show here. If this wave propagates and interacts with this bottom for a long time, okay, you have no reason to understand this now. You just have to believe me. And sometimes I repeat some of this seminar at the end of the course, and you will understand much better what I'm saying. So that's a little bit of a fun thing too. Okay, is that as this wave interacts with this bottom, it looks like it's under a diffusion, which there's no diffusion coefficient in the PDE. So it's called an apparent diffusion. Apparent because it looks like a diffusion, but it's not a diffusion. But here's a little bit of the physical intuition. You have no idea to understand it from a mathematical point of view, but a physical intuition why there's something like a diffusion. Because look at this graph here done numerically. Okay, so this wave, as it starts propagating over this, and if it propagates over a very long distance, so in the probabilistic sort of theorems that with my colleagues we kind of use is that this is on a scale, for example, epsilon. The wave is a scale, reference scale 1, and the propagation distance is on the scale 1 over epsilon. So you have a microscale, the topography, an intermediate scale, which is a mesoscale, the wave, and a macro scale, which is the total propagation distance, which the wave sort of interacts with the bottom, and something slowly builds up, which is the apparent diffusion. How is that? Look here in the numerics. Here's this wave. I can guarantee you, maybe I have another transparency I forget now. This wave here is already smaller than this one and broader. It looks like it's under diffusion. So it's kind of losing energy in a diffusive-like manner, right? And why is it losing? Because there's this, what we call multiple scattering, right? which from the acoustic point of view, we can call it like almost like a reverberation, which is an echo that goes back and forth, back and forth. That's an intuition, okay? And you can see it here. Look, this part here, which is over the topography, the topography is indicated here. Here's 0, which is here. This part here, this arrow indicates it's going back and forth. From this snapshot, this photograph, I cannot tell you here if the wave is going forward or backward. This part is going forward. And this part here is the reflected wave, which we can think from the acoustic, which is like the echo, right? If I scream here, oh, somebody might listen a little bit outside, which is the transmitted wave. And there's the echo that comes back. This is like the echo. So this part here, since it's over the part which the depth is constant, I know that it's a wave moving to the left. Okay? Very good. So here there's apparent diffusion, and then there's another spectacular phenomenon that was discovered, and done many things in Papanicolaou with collaborators, did many theories for acoustic waves, and with Jean-Pierre Fouque and Jocelyn Garnier, we started doing it for water waves, which is called time reversal refocusing. So if you forget all this, so first thing, so look at this signal here. It's a crazy signal. So it's a random signal because it was generated by the random topography. That's intuitive, okay? So there are many things that people can prove, whatever. I'm not a probabilist. I don't prove the theorems in probability, but like this signal here is mean 0, blah, 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 because this topography is mean 0, right? But look, this is fantastic and non-intuitive. If you get this signal that was moving to the left, and if you use like a hyperbolic equation, it's like if you put that information that's on the characteristic that's moving that way, and you then stop the problem and do the time reversal, which is basically just saying, okay, this guy that was moving this way is now going to move forward, is going to move the other way, but backwards. What do I mean backwards? The last guy that was generated is the first one to go in. Okay, so it's like putting a reverse gear on a car. And this is fantastic. PDEs-wise, this is the same as saying this guy was on this characteristic that was going this way, and now I'm going to restart my problem, and I'm going to put that data as my initial data going that way. You know what happens? In this crazy signal here, there's information of the form of the tsunami. So this guy, as it goes back and interacts with the same random coefficient, it generates a copy, a mini copy. Why a mini copy? Because there's only part of the energy. A mini copy of this wave here. So that's a time reversal refocusing. It sort of reorganizes itself into a copy. Okay? So some asymptotic simplification. So maybe in the end of the course, when we'll have more information, I might come back to this and give you a little more information of this. We'll see. There's many transparencies here, and I'm not going to rush. Probably this week is going to be more like easy picture, because it stimulates our intuition for what we're going to do with the PDEs, okay? And it's good that it's recorded. You guys can see. So what do I mean? This we're going to see in the course. Asymptotic simplification of differential equations. Okay? So how you get an operator in an intelligent, educated way, thinking of the modeling, you simplify the model to something simpler in the sense that maybe you can do mathematical theory, or it's better to do computations, but it's still physically relevant for the problem you're interested in, and it's still mathematically challenging and new. Okay? So this is reduced modeling. Okay? So one way I was able to get a model that I could share with my probabilistic friends, knowing that some of the limit theorems would work, was doing first a reduced modeling. So we're going to learn how to solve, right, Laplace's equation. So the water wave problem is more complicated than Berger's. We'll have free surface conditions here. We have Laplace's equation here. We have a Neumann condition here because it's impermeable, which means the speed is 0. There on the bottom, the normal speed is 0. But this is a crazy domain to solve Laplace's equation. It's a crazy domain to do asymptotics. But because it's two-dimensional, and because we're going to work with a velocity potential, so what does it mean, the velocity potential? Well, this is a potential, right? The gradient of the potential gives me the horizontal and the vertical speed. this potential, because the potential is a harmonic function, satisfies Laplace's equation. That's how Laplace's equation mixes with waves, as I already promised you, right? So nice. But then, the way I was able to derive a good equation for a rapidly varying bottom, which didn't work before, was using complex variables, using conformal mapping. So conformal mapping, very useful here, and there's a very nice tool you can do it numerically. And these curves here are the coordinate system in the conformally mapped domain, which is, I might give you more details as we move along. Think that I get this domain and I stretch it onto a uniform strip. On the uniform strip, this curvilinear coordinate system is a Cartesian coordinate system, right? So, but look, if we have a harmonic function, which is the real part of some analytic function, whatever, and I do conformal mapping, it's still harmonic in the other domain, right? Complex variables. So that's an excellent news, because it means it solves Laplace's equation here and there. Okay? So those are tricks. Here, it's just loose information for you, and this I don't guarantee we're going to get to this, but there's a chance. It's a candidate for us to study and learn more detail more at the end of the course, okay? So you use complex variables, and with complex variables, this coordinate system makes things easier. I cannot tell you right now why, but you'll see a little bit why in the future. And I was able to do many things and prepare the model, prepare the PDEs to be able to do certain things that later on we were able to do with using the probabilistic modeling that my other friends were experts, okay? Very good. So here is a model that you will learn how to deduce this model, but for a flat bottom is not that difficult. We're going to learn it without using complex variables. So basically we start with potential theory, we have Laplace's equation, we have a complicated bottom. At the end, let's think, you will see this for a flat bottom. We're able to, using Laplace's equation and the structure of a harmonic function, to reduce the problem for long waves, okay, which means the depth is small compared to the wavelength. We're able to reduce in an asymptotic way the dynamics to only the free surface up here. Okay, so look, this has basically only one spatial coordinate, which is C along here. It has a variable coefficient, this M, which has information of the depth and information that the problem is harmonic, blah, blah. And at the end, we have a system, which is a Boussinesq type system. You will learn how Boussinesq, this French scientist that did many things, why his name comes into this model. And this is a system of two equations for U, which is the average, for example, could be the average horizontal speed. Here it's not quite the average. And eta, which is the wave elevation. So this is the fluid speed and the wave elevation. Everything controlled only on the free surface. So that's an interesting thing. Not only it's asymptotics with a differential operator, but it's also very good for numerics and other things, because I was able to transform mathematically a 2D problem into a 1D problem. So that's good for theory, and that's good for numerics, right? Less effort on the computer. Good. Here is the acoustic problem, which is a problem studied by Papanikolaou and collaborators doing many, many things, including proving limit theorems for differential equations with random coefficients and so on, okay? Some very important thing. So I'm going to show you this problem on the backboard later on. This is a linear equation that looks very much like a simplified version of the water wave problem. This is a hyperbolic system. Okay, has characteristics, one in each direction, like the simpler shallow water problem has. This I will explain to you maybe next week. Okay, we're going to get to that soon. But let me explain you the acoustic problem. How is it done? And this problem, because of one thing, got super complicated. There's actually a book now by all these people I mentioned, Papanikolaou with Jean-Pierre Fouque, Jocelyn Garnier, and another former student and colleague also that was here at IMPA, Knut Sona. All of them have been here at IMPA, the authors of this book. So what is this problem? Think of this. This is the, I put this tree just to say this is the crust of the surface of the Earth, right? And the model considers that the Earth crust is layered. That's pretty good, pretty much a good model. Definitely if you see pictures of the Grand Canyon, you see that. But even if you see here around Rio in Brazil, if you cut a mountain, you see that it's sort of like layered, right? So that's good. So that means that the most simplified model, which as you will see is already very complicated, is like this. Think that Z is coming down, so you have Z and T, okay? This is a layered model. This could be an oil reservoir. These are different types of geological material, right? Clay, sand, rocks, and da-da. And that makes the speed piecewise constant, because it's constant over each of these layers, but random. Random is a modeling option. Like if you're looking for oil, you don't know what's there. So, you know, geological people know how to probe, you know, they know how to make holes and get samples, but then you say there's some uncertainty because I don't know if what's underneath here is the same that's underneath you, right? And I need to find oil. So it's a very good thing to study mathematically a problem with uncertainty. Where is the uncertainty? So the uncertainty is actually in the speed, but it comes out like this. P is a pressure, so you have a pressure wave here. There's many ways to try to find things, which is they use sometimes dynamite, sometimes they use a truck, which is a truck very heavy that puts itself up and pounds the ground. So it's like I'm jumping here, I'm generating a pressure wave down that echoes, comes back because there's different things below me, and it propagates. And in geophysics, they put what's called geophones, which listens to the echo and gives you a profile of, you can infer the profile of speed of propagation. It's a very complicated problem, and I'm not an expert, but that's how it works, right? So the PD to study the direct problem, which is how things propagate down, is like this. Pressure wave and speed, right? Speed that things are going down. So this is like a bunch of matrices, one on top of the other. You're a kid, you like to jump on the mattress, you jump on top, but there's different types of mattresses, and you know, the pressure wave propagates down differently, and something comes back up too, right? So you have a downgoing wave and an upgoing wave, okay? But you have the complications that you have rapidly varying coefficients, which are here. The density of each of these materials, and see it's Z over epsilon squared. That's the scaling. If something is epsilon is small, this is a rapidly varying coefficient with respect to the solution of the PDE, okay? And 1 over kappa, or K, is called the compressibility. So this is like the density of the material, and this is the compressibility of these matrices. And these are variable coefficients, which you can model them as a random coefficient, right? So if you think it, you know, so you can go to stochastic processes, whatever. This is in the numerics, you do a realization of this random coefficient and do a test, and then do another one. There's many things you can do, okay? And mathematically, it's very complicated. So you have to say things about the solution in some way, okay? So for example, the work of Papanicolaou and the theorems and so on is that they have a theory, they have some theorems that will say for this system, what is the expected value for P under the influence of these random coefficients. Highly non-trivial, beautiful theory, okay? We're not going to see this in the course, but no, I'll give ideas, right? Of how, at least what we looked numerically, what things we done. Okay, so we're going to learn soon that how do we compute this propagation speed? It's very simple. That has to do with the eigenvalues of this problem. And for this problem, it's basically here. The propagation speed of the wave is the square root of kappa over rho, right? You write this in matrix form. It's very simple, okay? And because these guys are real, this is called a linear, it's a linear system. Look, it's a linear system, not even quasi-linear. It's a linear system, and it's hyperbolic, has two characteristics. One going, in particular, usually one going to the right, one going to the left. Here's actually one going down and another one going up, which has to do with transmitted waves. You can control the transmitted wave, and you can control the reflected wave, okay? Right? Intuitive up now, right? You're not seeing the math details, but intuitive. If you have questions, okay, please ask. And the data is given at the point 0, right? Which is this pulse that will start propagating here. So it's like if you explode a dynamite, it's a very rapid pulse because like pressure goes up and down very quickly. Okay, good, makes sense, right? And if you actually want, and you can see this in the books, you can actually put here a Dirac delta function, which makes it even faster, let's put it this way, right? The scale disappears, right? All right? Okay, this problem can get even more complicated. You just got to go to the computer and so on. But here there's like some theory and computation. So this is a model for oil. It's even more sophisticated than the one I showed you because now it's 2D, right? It has a name, which is named sort of, I think this model was sort of invented by the French Institute for Oil Research, whatever. They call it Marmouzy. First time I heard this, I thought it was a place somewhere called Marmouzy. I forget now the reason of the name. This is a synthetic model. So it means synthetic model means somebody did it artificially, but very realistic. So let's see, why is it very realistic and very complicated? So this is a 2D model. So I put this just to illustrate, right? I put this tree here, and this is where the delta function would be, right, the pressure. Now look at the color code. This is the propagation speed of the medium, right? If you have rock, solid rock, sound propagates faster than on sand or water or oil and so on, okay? So they did this model. It's beautiful. Not only it's beautiful looking, but it's interesting physically, mathematically. Why? It's layered. So it looks like the other one, but it's more complicated because now they added faults, right? Geological faults, which means something slided over time, right? So it's layered, but it has faults. And, it's tilted, very complicated, but it looks realistic. So it's good to test mathematical models, direct mathematical models, and inverse mathematical models. So direct mathematical models is solve the wave equation, for example, in this crazy medium, where this is a pictorial, means colorful, indication of how the coefficients vary. You agree? How propagation speed varies, right? And you can also do, here's like French Petroleum Institute. And you can do also inverse problems, which is pretend you don't know what's underneath. That's what you do. You get the reflection, and you try to discover if this is sort of an oil reservoir. I don't know if that's the case, but try to discover where it is. And there are two types of very difficult inverse problems. The first one is imaging, which is to image where something interesting is. And the other, even more complicated on the class of inverse problems, is really do the inverse problem to sort of try to discover from the wave that came back how is this propagation speed, or what is the variable coefficient of the equation, which you don't know what the variable coefficient is. You just know, say, if it's a wave equation, what is that's very complicated and very difficult to do. Okay. So numerically, look what they did. I'm going to show you now characteristics. This is a 2D, the model here is a 2D wave equation, okay, with a variable speed. What is the 2D wave equation? It's the 2D wave equation we learned as an undergraduate, right? The D'Alembert, which is UTT c squared uxx equals 0, but it's not uxx, it's Laplacian u equals 0, okay? But the c, the velocity, is a variable coefficient that depends on x and z in a very complicated way, and with discontinuities. Okay, this was a talk I saw, a very nice talk I saw in Stanford at a summer school many years ago that Papa Nicolau organized. This person was a person from I think, Shell in Holland, a researcher at Shell Holland, and he showed these pictures. So here is the domain, and look at this. These are the wave fronts. Remember I was mentioning of wave fronts, like what you see from the airplane of the wave approaching the shore. Here's like wave fronts, but of what? Of pressure, right? So look, here is where the truck or the dynamite was. This region here is pretty much homogeneous. So it looks like a circular wavefront, just like when I let a rock fall in water, right? You get the circular wavefronts. Or now when I'm speaking to you, right, there's a sort of spheric acoustic waves, right, that's propagating towards you. There's no really barrier, so you all listen to me in the same way, and there's no echo, right? It's all going forward. So this is 2D. But then, when there's complexity in the medium, look what happens. And these are regions here where we see caustics. What are caustics? As I showed, it's like converging characteristics. So we're going to learn, so here somehow this could be solved numerically using the Icono equation, right, which I presented to you. And in the next Blackboard class I give to you, which might not be Wednesday, maybe I start Wednesday, we'll see how much time I'm going to spend here. We're going to learn how to solve the Icono equation, how to get the Icono equation from a wave equation, from here. So this is like the level curves of the Icono equation, and the characteristics are the rays. This is an approximation that we call geometrical optics. So you can think of this as you're shining something very bright here, and this is the index of reflection of the medium, and the light sort of varies in a funny way. And look, these are the characteristics. And look, what are these, what are these, what are these? These are the caustics. So just like I mentioned to, in the bottom of a pool, you see these bright spots because of the sun and the surface of the water acting as a lens to sometimes make the rays converge. Here the rays are converging because of the variable speed of propagation of acoustic waves. So these are the caustics. It doesn't necessarily mean that the solution blows up for this linear problem. It means that the intensity increases. Okay, and if you put both of them together, you see here the fronts and the characteristics, and you will see that for the Icono equation, the characteristics are orthogonal to the fronts. It's very simple to prove. It's very, 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 very simple. But right now, it's like, what are you talking about? Well, we haven't seen the Icono equation. We'll see this soon, right? Okay, so very, very nice. Now, going back to this, okay, so when I do the dimensionless problem, okay, when we do, right, the dimensional problem, parameters appear. As I mentioned, height over depth. So here are the parameters. I didn't mention. This alpha here is amplitude over depth. I mentioned that too. And beta is depth over wavelength. And look at this. This parameter here, which could be an epsilon, could be a small parameter, tells me how nonlinear is the problem. Oh, why amplitude over depth tells me how nonlinear is the problem? I mentioned that the tsunami, the amplitude over depth is 1.5 meters over 4,000 meters. So the tsunami, when it's generated, it's a linear problem. And on the other hand, in your bathtub or whatever, or in a puddle in the street, you might have a nonlinear problem because it's very shallow. Right? How do I know that this is a nonlinearity? Because of here, look, alpha multiplies all the nonlinear terms. Nonlinear, nonlinear. Okay? And beta, we also call it the dispersive parameter. That you don't know, you don't have to know right now. We have to look at things in Fourier space, but it's because it multiplies these guys, which are higher derivatives and which have to do with dispersion relation, which is something we see in Fourier space. We'll see this soon, okay? Just believe me. But this parameter tells me how long is the wave with respect to the depth. So when we say we're in the long wave regime or we're in the shallow water regime, it's exactly the same. It's just whatever terminology you prefer, okay? And we can take sometimes what's called the shallow water limit, which is letting beta go to 0. Then the equation becomes hyperbolic. Mathematically, there's no problem. It's perfect. It's actually interesting to do that. And sometimes you get, for example, when we write a paper or so on, referees that complain when we say we do the shallow water limit because it looks like the water depth is going to 0, and they prefer, oh, it's okay. Not everybody complains. They prefer that you say the long wave limit, which means the wavelength goes to infinity, right? Still the parameter goes to 0. It's just a matter of terminology, and in the jargon, shallow water limit is well accepted, but sometimes people prefer to say long wave limit, right? But you see there's no difference. It's beta going to 0, Okay? So here, so solitary waves, the famous solitary waves, we're going to see I'm going to deduce for you the famous KdV, which is the famous Korteweg-de Vries equation that has a solitary wave, has many, it was important for many, many things. I'll mention that. And that equation is deduced, is basically for alpha, appears for alpha equals to beta, order epsilon, no variable coefficient, and you have to reduce the system. The KdV equation is a unidirectional equation, which means only waves propagate in one direction. So we're going to learn how to reduce this system to the KdV. Also part of our exercise. We'll see this in the course. That's a guaranteed promise. Okay? There's another thing, which is why the formulation, the potential theory formulation is very, very interesting. It's because it's what I call the mother equation for many famous equations. I can derive from potential theory, which we're going to see potential theory, I can derive Boussinesq equation, KdV equation. I do this in this course and in the fluids course also. And we can also derive, and usually I don't do in the course because there's not much time, I can even derive the famous Schrödinger equation that appears in quantum mechanics. Schrödinger equation, KdV equation appears in many situations as a sort of a very common leading order model. And the Schrödinger equation appears when you do a modulation theory for a wave packet. So what is a wave packet? We see that in the ocean. Is when you have a wave train, which is a bunch of waves coming in. And actually, if you go to the beach to do surfing, body surfing, whatever, when the waves start coming in, right, you wait a while, there's no waves. And then the experienced surfers, they know when the wave comes in, the waves start coming in, you know, there's a wave train coming in a few minutes. They usually do not catch the first wave because there's a bigger one coming a little bit later, I mean, a few seconds afterwards, right? So this is a wave train, and when you call amplitude modulation, is because you have this amplitude that modulates the wave, and the Schrödinger equation is an equation that wants to track the evolution of the envelope. Okay, so it comes out the same sort of nonlinear Schrödinger equation. Schrödinger equation is the one you see in optics, and actually when you have a solitary wave in optics, it is a modulated solitary wave. Well, you know solitary waves in optics is very important, right? It's how we communicate over a fiber. Internet or fiber optics is pulses, right? And a pulse is a little bit like a bit stream, we call it. Like a pulse is a 1 and no pulse is a 0, and right? So it's very important to understand optics related to pulses using the Schrödinger equation. It's used for, right, to understand things related to fiber optics. Okay, another thing that I wish I knew more, I'm not an expert, but very interesting application with very good books by actually authors that are very good, actually, many of them, including Complex Variables book. One of them is Abrovitz, Focus, and other people. So these names will come up. Okay? Now, effective behavior. I already commented a little bit to you on what effective behavior is, like the apparent diffusion, right? So maybe from the time as we're going on, I think we'll see. Maybe we'll get most of the slides done today. We'll see. So effective behavior. Apparent diffusion. So let me get back a little bit more to apparent diffusion. So it's asymptotic analysis of solutions. So these things are a little bit come together, okay? Many times it comes together, which is I talk about asymptotic analysis of differential operators, which is I put the epsilons here and there, I can average some terms. We have to learn how, in an educated way, to drop terms from the PDE, not just dropping. I mean, some people are very good, and a long time ago they would just drop based on intuition, right? This is not important, that is not important. But sometimes it's better to do it in an educated way, which means you dimensionalize things, you see where epsilons are, and say this is a dominant term, this is a secondary term. So that's sort of, some sense, asymptotic analysis of the PDEs. But then, sometimes you have a PDE, and homogenization is the case. I'll talk about homogenization very quickly at some point, is that you have a PDE, this and that, and you want to see the asymptotic behavior of the solution. The solution is very complicated, and you want to get the leading order term of the solution. So the differential operator is there. And I'll show some of this to you. What is the leading order? How does this, as I mentioned, this course, differently from another important course, which is the function analysis course, we want to always, in some sense as possible, to see how the solution looks like, right? In functional analysis, you prove the solution exists, that it might have a certain number of derivatives and so on, very important. But sometimes you don't see how the solution looks like. So we have to do this approximation sometimes, which is asymptotic analysis of solutions, which means I'm not touching the differential operator anymore, touching the sense I'm not simplifying or anything, right? So, so this is, okay, so I forgot to say, so O'Doherty and Anstey are two seismic researchers, do seismic analysis. Seismic analysis seems it's related to earthquakes and so on, but actually people who study geophysics related to petroleum and so on, to oil recovery, do what's called seismic analysis, but because you send this pressure wave and so on. So there are two guys related to this. And in 71, they realized that as a wave, right, they kind of tried to explain, as a wave propagates over this randomly layered medium, they were what he called apparently attenuated. So if you had a wave equation, as we saw, a wave equation looks like the pulse. Remember, the first class is that we had a pulse that was like a wave of translation. Didn't change form or anything. But when it's kind of on this quote-unquote bumpy road, there's like reflections and so on, it starts losing energy to the reflected waves. And depending on the regime you are, this loss of energy to reflected waves, which is like echo for acoustic waves, might have a certain behavior, right? It depends on the scaling. What do I mean? For example, if the variations in the medium are on the same length scale as the wave, the behavior is different than when the variations of the speed and the coefficients is on a smaller scale with respect to the wave, which we call the microscale. So you got to define in which regime you are, so you can then do some theory or numerics and understand the behavior. So O'Doherty and Anstey said, look, it looks like we're under an apparent attenuation. They didn't quite call it apparent diffusion. So somehow the waves are being attenuated in a regime that first we thought they shouldn't. And it was due to, but they kind of kept their shape to some extent, right? The form of the wave, it was like a pulse. The pulse started broadening and decaying, so like it's being attenuated. But there's many ways to do attenuation, right? If we're going to see this more, if we're studying a differential equation, a wave equation, you can attenuate a wave through damping or through diffusion. Right? We'll see this later on. There are different terms. One is minus a constant times the function value, or the other one is second derivative. The different type, they affect in a different way. So it was understood that for the case of the acoustic waves, that it was diffusion-like, which meant that it looked like the waves were being attenuated as if, that's why it's called an apparent diffusion, and that's why sometimes it's called effective, that to leading order, when I say effective, it's like to leading order, it looks like the equation has a diffusion coefficient, but it doesn't have a diffusion coefficient. There's no diffusion coefficient. But the diffusion coefficient is due to this multiple scattering, this diffusion coefficient, or this diffusive behavior, sorry. So it's this bumping. So that's what this is about. Let me show you a little bit about this. So let's go back to that figure, right? I already announced this. So as I mentioned, as this wave interacts with this long medium, little by little, so it's like the wave feels a little bit of an obstruction. So it passes, but there's a little bit of an echo, very small, that goes back. And then there's that again, and again, and again. So this is what generates what we call, what's called the wave coda, like it's a bit like the wave tail, right? The wave coda. So you see, there's all this amount of wave energy that was removed from the wave front, right? So we call this the wavefront because it's the front. And it's still, you see, the wavefront still retains the wave shape, meaning the shape of the initial condition, right? But it's losing energy, right? It's losing energy to this whole guy behind it. Slowly, but it's losing energy, okay? Okay. And then this is the reflected wave, and I said this is the transmitted wave. And this is where the disordered microstructure topography is. Now, the claim, okay, which I'm going to show you a little more detail, but you're not going to understand everything now. But at the end of the course, you might, as depending on what I give you to read and so on, is that this wavefront here seems to be under what's called the apparent diffusion, which it looks like the PDE has a diffusive term, but it doesn't. Okay, so how does kind of one see that and actually characterize that mathematically, the apparent diffusion, okay? So I'll give you a little bit of a mathematical idea of that, but just a little bit. But as I said, if I repeat some of these slides at the end of the course, you say, oh, now I understand what André was talking about. But that's normal, I haven't taught that. But this is just to see how we're going to evolve in the subject. So look at this. So this is an initial pulse, which is a Gaussian, initial profile. And this is actually some computations that actually I did with Juan Carlos Munoz, which was actually my first student at the end of the 90s, right, the early 2000s and so on, when he finished his thesis, I think 2002. We used the Boussinesq system. The details is not important. Here's some information, Riemann invariance, blah, blah, blah. You're going to learn about Riemann invariance soon in the course. But let's forget about all this detail. Let me just tell you what the numerics are doing. So here we first tested if the numerical method that Juan Carlos was using was good. We got ideas from a paper for this equation, and we wanted to see if the numerical method was good. In what sense? This is not a numerical methods in PDE course. Sometimes I give this course. But I'll show you a little bit, just a little bit, that sometimes a numerical method has numerical diffusion or numerical dispersion. You still have to learn what dispersion is. Which is many numerical methods, even for ODEs, is very simple. So it might have a numerical attenuation. So for ODEs, it's even better. Take a harmonic oscillator, right? Something just mass spring oscillating. When I solve it numerically, it might have, it's easy to show, I might show you someday in the future, it might have numerical damping, which means it slowly goes to rest. And say, wait a minute, the equation didn't have damping, but it's easy to see it's numerical damping. It's due to the numerical discretization in time that sort of attenuates the oscillation. It's not difficult to see, okay? So in waves, you can have numerical viscosity, numerical diffusion, and so on, okay? So we wanted to test, I told Juan Carlos, let's make sure that the numerical method does not have numerical attenuation, right? So we also can find the proper discretization, time step and spatial stepping, so that we don't, so Juan Carlos did a uniform medium, which means flat bottom, okay? It had, and he put a wave, a pulse, and let it propagate, and we know that the pulse propagating in the proper regime, like a solitary wave, propagating over a uniform medium, it's a traveling wave. You know now what a traveling wave is. It's a wave of translation. So this pulse should propagate without changing its shape. And we would know that the numerical method is fine. So here it is. This is our first test. Initial profile plus traveling wave. We put one on top of the other, you don't see a difference. So cool, that's good. Okay? Which means for the flat bottom case or for constant coefficients of our PDE, we have a traveling wave as it should be, so a solitary wave. Now we put our random coefficients, right? Using the random number generator of MATLAB, we put a synthetic random topography. And look what happens. Here in the front, you can see the effect of what I'm calling the apparent diffusion. Look, the pulse is smaller and broader. Just like in the heat equation, you see that the temperature, you will see that, maybe you remember this from undergraduate, but we'll see this again, because actually the fundamental solution of the heat equation is the Gaussian. So it makes the solution go down and to broaden. And here, in Fourier, we can show that to leading order, the transmitted wave is suffering something under the action of this Gaussian in a similar way to the heat equation. I'll come to that, I think, in the next few slides. No, it's already here indicated. So here is, look at this. So we were very happy when we saw this, because Juan Carlos did two things here. He did the computation with everything, with all the variation, random variations of the medium. You have to use a very fine grid, so very careful computation, and he got one of these curves. Okay? And then he got the theoretical approximation, which is a Fourier integral, okay, which is basically deduced in a paper, which at the end, the Fourier integral tells us something simple. Okay, the theory is not included. The theory was not the probabilistic theory. The probabilistic theory is even more complicated. We did a deterministic theory based on the paper, which I may mention to you when we get there, which is Berlin and Burridge, that says this. The moral of the story is simple, right? I mean, how to get there is not that simple. But it says this, that the transmitted wave in Fourier, which is t hat, so you look at things in Fourier space, okay, is basically the Fourier profile of the initial data. I put this multiplied here just to indicate it's like a convolution, but it's, in Fourier space it's multiplication by a Gaussian. So if you have a convolution, right, in Fourier space, it's basically the function times the kernel, the Fourier transform of the kernel. So look at this. Now I'm going to, the fact that I have that the transmitted wave, that one that's surviving, so this one, right? This is the transmitted wave. This guy, see the t? It's actually given by a simple formula, which is a convolution of its initial shape with a Gaussian kernel. Okay? Well, I can now use different words for the same thing, right? This is a purely mathematical thing. But I think there's a good way, that's actually the way Berlin and Burridge mentioned their paper, which is kind of intuitive. Let me say first, the first thing that explains why we call this apparent diffusion. The Gaussian kernel is like the fundamental solution of the heat equation. So that's why it's the apparent diffusion. So here it is. That's why the name is apparent diffusion, because it's the Gaussian kernel. Berlin and Burridge also mentioned that we can sort of call this a Gaussian filter. That also makes sense. Why a Gaussian filter? It's kind of a low-pass filter. You know, sort of a filter is something that filters, takes information out, right? Filter. So a low-pass filter is a filter that lets low frequencies pass and blocks high frequencies, right? So in Fourier space, it could be like a shape of a square like this, like an indicator function. If it's a Gaussian filter, it means it's a little bit like a low-pass filter. It means that the low frequencies, if you look at the one half of the Gaussian, it's like it lets the low frequencies pass, and it starts exponentially decaying the high frequencies, right? So here, this is like a low-pass Gaussian filter, which what does it say? It's saying that actually in these guys here, these guys that are coming back are the high frequencies that were not permitted to survive, right? So it's another way of putting in words the same mathematical result given by this expression. One, it looks like a solution of a heat equation. Also, you can think in terms of signals as a Gaussian filter, right? It's kicking back high frequencies, okay? And what was fascinating to us, me and Juan Carlos said, no, are we doing this right? We said, yeah, we're doing it right. What was fascinating is that this theoretical approximation, based on the paper of Berlin and Burridge, was that it was a nearly wavefront, not nearly, a near, proper English is near wavefront approximation. What does that mean? It's a good approximation only near the wavefront. But the asymptotics were so good, to our surprise, that it was better. It was a good approximation near the wavefront and even a little bit behind the wave. Let me show you that. Look at here. Here near the wavefront, one curve on top of the other, which is the numerical curve and the theoretical curve. And look behind it. I mean, here there's a little bit of a discrepancy. Do I care about this little discrepancy? No. Look, over here it's right. So that's really a gift, a bonus track in the sense that you're trying to do you're trying to do something here, and it's even better than that. So this is a comparison of the effective Fourier integral versus the multi-scale simulation. What does it mean, multi-scale simulation? It's a simulation with several scales. Micro scale, intermediate scale, and macro scale. We have to let the wave propagate for a long distance. So very nice. So some of these things we'll understand a little better by the end of the course, way to the end. But I can see in your expressions that at least the story, what I want you to see here is just the story and what does it mean, the applications that I intend to show during the course, okay? Now let me show you a little bit. I have a little bit still time, that's good. I thought I wouldn't have time. So show time a little bit of the time reversed refocusing, which was a spectacular thing at the time. It looked like, no, how does this work? It looks almost like science fiction, but of course it works. And my intuition didn't work. I mean, the mathematics helped one, at least me, to acquire intuition for the problem, okay? So let me show you some aspects of time reversed refocusing. So I said here, when I was teaching this, and it remains here for this course. I'm not sure we'll cover this in the course, but I'll show you in a very descriptive fashion, and maybe not even at the end of the course, we can see this in detail. But anyway, let's go. So this is a paper by Matthias Fink, a prominent French physicist, still very active in research, and that did this paper in 1999, Scientific American. If you go to the library, look Scientific American, November 99. This is a journal where it's more to tell people, right, in a general public what the work's about. And this figure here of this man was used by all of us, right, started with, I think, all of us in our talks of time reversed refocusing. And this cartoon here tells you a little bit, not in a very correct way, but it's a very good cartoon of what happens, and I'll tell you a little more, when you do time reversed acoustics in the acoustic sense, really in the acoustic. And with two French colleagues, one was Jean-Pierre Fouque, which was who's friends of Matthias Fink, also Jocelyn Garnier is, but at this time Jocelyn Garnier was just out of his PhD, and Jean-Pierre Fouque was his advisor, and Papa Nicola was also studying this. We were all trying to understand. They were doing work in acoustics, and with Jean-Pierre and Jocelyn, we then imported this theory for water waves. So what happens here? So here this cartoon says this. Imagine that I'm going to show you a picture which is like this. You have an acoustic room, which is like a studio for, right, acoustically sound room, where on the front, say this blackboard, you have transducers, which are this equipment that, let's put it this way, it can listen to what you're saying and reproduce what you're saying. So it's like acts as a microphone, which listens, and loudspeaker that sort of reproduces the sound. But it's connected to a computer that can do the time reversal. As I showed you before, the time reversal is whatever was recorded last is the first thing to be played back in the playback, okay, to be sent out. That's what time reversal means. So here, in this picture, this man said hello. This yellow part is where the transducers are. It records it, and then it sends it back. But actually, I've never been to this chamber. Jocelyn was, Jocelyn Garnier. And he says, you don't hear the word reverse. I'll tell you how you hear it. So if he says hello, it looks like here he will listen ole, but it's not ole, okay? But we'll see what happens. So this is a picture that I did that sort of reproduces what, say, Jocelyn that was there told me that happens in this acoustic room. So in this acoustic room, one person says hello. And the more echo, the more reverberation there is, the better. Why? Because the more reverberation there is, the wave, the sound wave, the acoustic wave survives, bounces, not dissipated, bounces, is that in this signal that's recorded here by the transducers, and in this systematic way, it's not only 4 transducers, but I'm indicating only 4 transducers. This is the last signal recorded. But in this signal, there's information about the geometry of the room, okay, to some extent, right? So then you do the playback. And what is fantastic, and Jocelyn told me this, is that when you do the playback, somehow the sound, the signals have information of the room, and they refocus at the source, okay? The source, which is here. It's an approximation, say, of a delta function. And look, here's which would be, I just mentioned, this his spherical wave, but in this 2D model is a 2D wavefront propagating out. Okay? So it will refocusing should take place at the source, at the single point, right? And if things are well done, Jocelyn tells me, and Matthias Fink, when gave a talk, said this, when he's like selling this technology, and in particular, this technology is operational, as I know, for many things. As I'll show you, from kidney stones, and there's a figure in this article about kidney stones, to trying to find tumors in people when it's still very small, which would be something very small, a tumor. In the random medium is our body, because it's heterogeneous, right? So what happens here is when you do the playback, the wave will refocus here, and the red person will listen something, and this is fascinating, and the green person listens nothing. But of course, the trick is that the playback has to be done in a very low volume, or else the green person will listen to noise. Okay? So what Jocelyn says is that the red person will not listen ole, right? It's not like that. But will listen to something which we call coherent. Maybe like a word you don't understand, from a foreign language you don't understand. Like a whisper of something you don't understand, where the green person won't listen to anything, because if you do the playback at a very low level, you cannot listen to the noise, which is the residual. Okay? And the crazy thing, too, is that because the refocusing comes from all directions, you have no sense. It looks like the voice comes from within, from inside of you, because there's no sense of direction, right? So it's fascinating. Very fascinating. So here's a picture from Matthias Fink's paper, the Scientific American paper, exactly mentioning what I mentioned to you. Here's the source. He puts some obstacles here. The obstacles deform the wavefront a little bit along the lines of geometrical optics, as I'll explain you in the next lecture as I go to the blackboard, maybe even next class, because I see I'm having much more time than I thought to talk about these transparencies. And then here are the 4 transducers that recorded the signal. And then the playback is whatever was recorded last will come in first. The wave somehow retraces its path and will refocus here at the source. That's what the picture of Matthias Fink is showing. Okay? Here is the case of how is it used to, a kidney stone, how to burst a kidney stone. So if you want to try to burst a kidney stone, there's many techniques. There's shock waves also you can use in a bathtub and so on, and sort of something like a bathtub and that. So you don't want to hurt the patient, right? So with the time reversal, what you can do is this. You send first a signal, a pulse of ultrasound, high frequency, It will reflect on the stone, which is the hardest part, right, than the tissue. It will come back, that's the echo. The computer records it, does the time reversal, and then the doctor has more information about where the kidney stone is, and he can put the intensity up, and it will refocus on the stone, so it's a much better chance that he will be able, in a few trials, to burst the kidney stone with his pressure wave. Okay? So this is one application that Matthias Fink was mentioning in his paper 1999, so more than 20 years ago. Okay? So let me show you the refocusing in my water wave problem. So we were trying to do refocusing here, and the good news here is that this was a natural problem for us to test other things, which were what? Matthias Fink, the problem was linear acoustics. So here we could do linear dispersive. You still have to learn what dispersive is. I could do also nonlinear refocusing, because the equations in water waves permit that. And we did that in the paper. So here's time reversal. I forget what I did before, right? And I send this guy back in. Okay? So I have to solve the same problem and see what happens. So here's the numerical simulation. Here's my crazy signal. This is where the topography is. It starts interacting. Look how things are starting to pile up, and eventually, boom, a mini copy of my initial data appears. Why a mini copy? That's clear, right? Because I'm using only part of the energy. And even though the limit theorem of the theory that Jean-Pierre Fouque did with the former student of this and so on, is that everything should refocus as epsilon goes to 0. In the computer cannot make epsilon goes to 0. So I have still a little bit of residual, but it's clear that I have a wave there. Okay? And this is the formula by Jean-Pierre and the student, and the expected value of the refocused wave, it's given by this formula. It has this coefficient, which is the expected value of the coefficients, blah, blah, blah. It's a Fourier integral. Okay? This is another simulation with this Gaussian pulse. And now let me compare you. Maybe I'll finish with that. Let me compare the theoretical formula that comes out of a limit theorem. So it's the expected value. Look, the expected value, I forgot to read this. The expected value of the reflected coefficient as epsilon goes to 0, where epsilon is the scale of the random coefficient. Okay? And it's highly non-trivial to show this, but the formula is easy to read. Look, it's the Fourier transform of the initial pulse times this guy here. Okay? And look at this. Here is the initial pulse. Here is the theoretical pulse refocused, and this is the numerical one. Bingo, right on top. Okay? And what does this shows is that actually that formula, that's another highly non-trivial thing to prove, is that this shape is independent of the realization. So here we did 10 different samplings of the medium, and look, the refocused shape is the same. The residual is different because it depends on the medium, the realization of the medium. But the shape of the pulse is the same, which is very nice. Okay? So I think this is a good point for us to finish. I did more than I thought, which is the time reversal part. Let me actually see, maybe I have one more thing. Let me see. Oh, yes. And the other thing, too, is that if the medium is very long, right, everything should come back to you. That's something that actually is famous in physics, which is called Anderson localization, which means a random medium is opaque to all frequencies. This was like a Nobel Prize in physics for, not in this scenario, right, in physics of particles and so on. And we can see that with these waves. Look, if I make here the time go to infinity, this becomes 1, right, if I let time go to infinity. So therefore, the expected value of the reflected wave is a copy of the original wave, because this goes to 1. Right? So we did this numerically with another student, Daniel Alfaro. So here's the input. We cannot see the wave here because this is so long. So the wave is this blue thing. That's that same wave. And look, the apparent diffusion. Very quickly, it's disappearing. And we're recording everything that comes back. So we send it back in. And eventually, a wave reappears. So you can't quite see a wave here. So I'm going to zoom in and look at this. This is the initial data, and this is the refocused wave. Everything came back. An exact copy of what was sent came back. The random medium threw it back. And this is related to Anderson localization. Okay? So I think it's a good point for me to stop here. I think there's still a few more transparencies that it's good, because I'll stop here and then I'll go back to the Blackboard next class. You know, and if there's a few more transparencies that I haven't talked, fine. We might come back to this at the end of the course, where you have been more educated to what's going on from the PDE's point of view. And that's the idea, right? The application. So I think it's a good point to stop here. And I think the story went well. At least I can see the expression in your face. The story went well, and we'll come back to this in the future, either through me or through you, right? Doing presentations, you'll see, understanding some of these things. So we'll finish here. Já acaba aqui. Obrigado.